For real this time. So yeah, 1 bit of information. And if we want to store, if we want to store more than 1 bit of information, well, that's actually not too bad. All we have to do is chain several of these things together. If I want to store 4 bits, 8 bits, 28 bits, whatever, I just chain them all together. Each one would have like a signal line. Because remember, we can only store 1 bit on one signal line. I know in digital we showed you how there was those mergers and splitters, but that's only for a visualization thing, to clean things up. At the end of the day, like each wire can only ever carry one signal, high or low. So each one of these would have some input line coming in and some output lines coming out. But if I wanted to store the pattern 0, 1, 1, 0, I'd have like 0, 1, 1, 0 coming in, and then I'd save it somehow. That's the idea. And if I wanted to have like, well, okay, I could store 4 bits, but what if I want to be able to store like multiple sets of 4 bits, right? I mean, we're working towards RAM. We know where we're going, right? This isn't a mystery. I want to be able to store sequences of bits, and a lot of different sequences of bits for whatever I want to use them for in the future. So how do I do that? Well, I just chain them together this way. Each one of these would have like a signal line coming in, you know, maybe like one signal line, like this is the, let's say like this is the 0 bit. It doesn't really matter which end we start at, like 0, 1, 2, 3, right? Or 0, 1, the 2s, the 4s, the 8s, whatever, right? I'd have like a line coming in that would like connect to each of these, because, you know, and then I'd have to have a way for my system to select, okay, like, imagine I have the pattern 0, 1, 1, 0, and I want to store it in here. Well, where, right? We know 0 is going to be in one of these, 1, 1, 0. But I need a way to be like, well, which row, right? So I'd have to have some control over like which row. And if I wanted to get information out, I'd need some way to control which row I want to output. But this is the idea. So any questions about this abstract, high-level idea? It's no mystery. Look, I know like we're working towards RAM, and we're like discovering how to make RAM, but we know where we're headed, right? There's no mystery here. We're building RAM. Memory, at least. And then I had this design. Again, let's not get too focused on what each of these boxes are. It's just some magical unit that can store 1 bit of information. And have a look at this. We can look at this and get a sense of what it's doing. We have data lines. So these are the signal lines. This, let's pretend this signal is like this, again, that 0, like the least significant bit, and then more, and then more, and then more, right? More significant as we go. And that line is connected to each of these, right? Because if I want to put in the pattern 0, 1, 1, 0, 0, 1, 1, 0, so each of these has like a 0 wanting to be input into here. But I need to have a way to be like, okay, actually input into which row? And we're going to do that with the decoder. Or we could do that with the decoder, right? Which row do I want? 0, 0? Okay, activate this row. Do I want the 3rd row? Okay, so that would be the pattern. Okay, like the 4th row, the 1, 1, right, 3. I put in a 1, 1, well, that would activate this row. So that's how I can like select a row. So each one of these has a 0, a 1 is like on this line coming in, ready to be fed into this memory. But then I want to be like, no, actually put it into this row or something. And in a similar way, we could do the output. These are the output lines. You know, again, least significant bit. Who remembers what these are? You don't remember? It's not a demultiplexer, it's a multiplexer, but you know, close enough. It's a multiplexer, right? We have the address line coming down to select which one of these do I actually want to output on that line. Which one of these, which one of these, which one of these? look, everything in this row, everything in this column is connected to this multiplexer. But only one of these rows I actually want to output, right? Like imagine in the top row I have 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0. Let's pretend that's what we have, okay? So at any given time, this one here is outputting this has a 1 and then 0, 0, 0, because that's what I said was in those respective rows, the last column, that least significant bit. They're all sitting there at the multiplexer, but with the address line, I can say which one of these do I actually want to map to that output. That's the idea. This is what we're going to work towards. Any questions about this idea? All right. All right. Now that we have a sense of what we want to work towards. But I was saying, okay, we have this magic way of storing information. How do we do that? And yeah, that's tricky. So that's what we're going to learn about. Latches and flip-flops. The first thing we're going to look at is a set reset latch, or an SR latch. Sometimes written like S-R, sometimes SR, sometimes you'll see it RS. It's a reset, set, reset, whatever. This is a very basic latch. But it's going to do something we haven't seen before. But it's totally valid, totally fine to do, but we haven't seen it before. This is the design. There are other ways we can make this. This is with NOR gates. But we could do this with other types of gates. They'll behave slightly differently, but the general idea is the same. And this is how this is a common way to represent it. Sometimes S will be on top, sometimes reset will be on the bottom, and these could be flipped, but it doesn't matter so much. This is the idea. And take a moment and realize that, what is the input to that top gate? The input to that top gate is R, and the output of this gate, right? By the way, aside, critically important, because you're going to have to do this on a test or something. When you're drawing, first of all, bring rulers. If there's a test, bring a ruler, okay? Because if I can't understand what you're doing, I can't understand what you're doing, and I'm not going to waste my time. But let's pretend I have a ruler right now, and we're drawing signal lines, okay? And let's say we're doing something like that decoder, right? Where we got 0, 0, and then, right? Whatever. And I've got these signal lines coming down, right? How am I supposed to know what's connected to what? Okay, this is obviously connected to this wire, and this one's obviously to this wire. But is this connected to this wire and this wire? I don't know. So we have a very, 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 very simple way to show this. Like that. Now I know where it's connected. Sometimes you will even see people do this. If you're ever worried about how clear your design is, sometimes you'll see people do something like this. Where it's oh, just jumping over. Make your designs clear when you're writing them. If I see something like the first one, I'm going to assume that you don't know what you're doing. And it's going to be wrong. I need to know that what you've done is very intentional. Otherwise, I'm going to assume there was no intention behind it and that you're just writing crap down or drawing crap down. Do you have a question about what I mean here? You've been warned. And it's on video. All right. back to this. You'll see here, even in the digital designs, like they do that, right? Like, oh, it's connected here. Not here because there's no like dot. It doesn't do that little jump thing, but that's fine. I think it's pretty clear. So this is a tricky one here because there's like a feedback loop on this. By the way, if you've ever had me before, like things get interesting when things become like self-referential. That's where like, you know, really cool stuff happens. But anyways. Okay. Oh, here we go. Okay, there are several possible designs for an SR latch. The textbook uses similar design to above, but uses 2 NAND gates instead of NOR. Although this NAND base design would work slightly differently, the general idea is the same. Like I just said, you can create this functionality in a similar way. The SR latch is not specifically this design, but the functionality one gets with a design like this, the behavior. Okay, so in an SR latch, S stands for set. Set the stored bit to 1. R stands for reset. Clear the stored bit out. Now, you might say, well, set, why don't you give it like a name like a 1, 0. Set it to a 1, set it to a 0. And you're entirely right, but a lot of these designs come like before like we built computers, right? So like designs like this are like ancient in the world of computing. And so a lot of like labels and names for things made sense at a time based on the functionality that they had, and they just stuck around. So there's like a lot of historical reasons for some of this stuff. Don't get too hung up on it, okay? Like this stuff wasn't designed to build a computer, okay? It was designed with like, oh, look what we can do, and next thing you know, we got other stuff. Like Q is the value of the bit being stored, and not Q is always the inverse. All right? So based on this, the way I want it to behave is if I turn that on, I want Q to be set to 1. Wait, no, not that one, set, pardon me. If I hit set, I want Q to be outputting 1. If I hit reset, I want Q to be outputting 0. And by this design, Q naught is always the opposite of whatever Q is. So if this is 1, what should Q naught be? Very good. In some of these designs, you won't even see the Q naught part because it's like implied. All right. Since the circuit has some feedback, its behavior depends on the current state. All right, so let's look at this table. There's a lot of different cases here. You'll notice, though, that, like, okay, there's 4 possible inputs, right? SR and then the outputs. But if there's 4 possible inputs, shouldn't there be 16 rows in this table for all possible combinations of the 4 inputs? Shouldn't there be? But there's not. There's only 8. Who can tell me why? This isn't a trick question. This is like the inputs, okay? Because remember, yeah, you're like, well, Q and Q naught. Let me take a step back. Let me make sure it's a little clear. Here's how I have this designed. S and R, those are clearly inputs. Right? And Q naught are the outputs, but they're also the inputs. So how am I going to do this? Well, take it easy. We're not there anymore. So we're treating Q and Q naught as inputs, and then Q prime and Q naught prime, or not Q prime, is like what it'll change to. So if this is the current state of the output, and this is like what happens, this is what it'll change to. All right? So why do we not okay, so there's 4 inputs, S, R, Q, and not Q. So why is there only 8 rows and not 16? Well, it's not possible to have the case where these are both 0. And similarly, it's not possible to have the cases where these are both 1. Why? They must be opposites of one another. These are not independent. They are entirely dependent on one another. So yes, there's 4 inputs, but one of those 4 inputs is really just tied to another one. So it's not really 4 inputs. It is, but they're not independent. All right? So if S is 0 and R is 0, and this is the state, nothing changes. If Q is 0, not Q is 1, and neither of these are set, these are not changed. Similarly, if Q is 1 and not Q is 0, these are not changed. Then, okay, if we set this to 1 and reset is 0, and 0, 1, well, this changes. What's the asterisk? Do I say what the asterisk is? And it's for emphasis later. There we go. Okay, we talk about it below. If set is 1, R is 0, and Q is already 1, it's unchanged. If we turn on reset, and it's already Q is 0, it remains unchanged. But if we hit reset and Q is 1, it changes. I think this might supposed to be a 1, 1. I think that's supposed to be 1, 1, right? 0, 0, 1, 0, 0, 1, 1, 1. Yeah, I think that's supposed to be the case. And then, when we have the case where we set and reset to 1, this functionality is not defined for a set reset latch. So it will behave the way it behaves, but the abstract idea of a set reset latch is not designed for the case of setting and resetting at the same time. That has undefined behavior. All right? FYI. And then similarly down here, although I'm pretty sure that was supposed to be a 1, so I think that's a typo. If they're ever both 1, and no matter what the output is, it'll set Q and Q naught to be 0, 0, which doesn't make any sense. Because well, how could it ever be? And it's an unstable, undefined state. Set and reset, the SR latch, really we want to be able to do nothing, set or reset. Doing both at the same time isn't really something we're supposed to do or we want to do. All right, in the above table, Q and not Q designates the state before changing S and R. Q prime and not Q prime designate the state after changing S and R. Also note that Q, Q naught can never be equal. That's why we have only 8 states, right? We've eliminated the states for when they match. When S and R are both 0, the output state of the circuit will not change. So if neither of them are set, I know I shouldn't say set. If neither S or R are high, the state of the system remains unchanged. If S is set to high, one of 2 things happen. The circuit may be in a stable state, meaning the outputs do not change. This will happen when Q is already 1. So if Q is already 1, and I try to set it, nothing changes. It's already 1. It's like I'm telling the thing, hey, output 1. It's already outputting 1, so it's like, okay. It's not going to change anything. That's the idea. Alternatively, the circuit may be put into an unstable state. But this unstableness is very brief. And when I mean brief, when I say brief, I mean like on the order of like nanoseconds. All of these signals moving does take time physically. And the transistors take a moment to like activate. But very, very small amounts of time. So these things are unstable, but only for a brief amount of time. So the output of this state is emphasized within the system. So that's this one here, right? Okay. Let's think for a moment. Okay. Let's say this is a 0. All right. Maybe let's draw this out. All right. R, S, oops, what am I doing here? And that's Q naught and Q. Okay, that's the set reset latch, okay? So if this is 1, but that's 0, okay? Right? So the output of this gate is 0. At this instant, it's 0. So let's pretend this is our reality, then we hit pause. Okay? I hit this, turn this to the 1, and the moment I turn it to a 1, I hit pause. This is what's going to happen. Okay, if this is 0, this must be what? 1. Right? And reset, well, that's 0. Okay? So, 0, 1. 0 or 1 is what? 0 or 1 is 1. And what's not 1? 0, right? So NOR is 0 and a 1. We see, I realize this might be in people's way. Is this helpful? Yes, you could have said something. Next time, say something. So 0, 1, 0 or 1 is 1, and what's not 1, 0? Because this is NOR, right? So it's an OR, and we not whatever that is. So this immediately turns to a 0. And then here, that means this input is a 0, and 0 or 0 is 0, and then this turns into a 1. But that now means that the input to this gate is now different. It was just 0, 1. But the input to this gate is now a 1. What's 1 or 1? 1. What's not 1? 0. The output stays the same. So the input changed, but the output stayed the same because it's still, that's how that function worked. So do you see how it became unstable for a brief moment, where because the output of this changed, it changed this, would change this, would change this, but that stayed the same? So there was a moment where it was unstable. Now, okay, great. Let's say this is now the state. This is still, okay, that's still a 0, that's a 1, right? Q is 1. Okay? If I turn this to a 1, what happens? 1 or 1, that's 1, not 1 is 0. Oh, that doesn't change, which means that doesn't change, which means that won't change, and then, oh, so nothing changed. It was already stable, nothing changed. Now let's play the game where Q is, okay, Q is 1, not Q is 0. Let's reset it. Okay, so let's turn this to a 1. 1 or 0 is 1, not 1 is 0. So that changes. So we're now unstable. 2 is 0. So Q becomes 0. That becomes 0. This is still 0. 0 or 0 is 0. Not 0 is 1. This turns into a 1, which means this input here turns into a 1, but that's stable now. The input changed, but the output didn't change, which means the system is now stable again. And the Q and Q naught switched. All right? And if this is the current state, and then I set reset to 1 again, what happens? 1 or 1 is 1, not 1. Oh, nothing changes. It's stable. So once Q is 0, I can spam reset. Nothing's going to happen. It's stable. Now, I think I spooked somebody outside. They're like, what's going on down there? Now, we talked about what happens when they're both 0. Well, look, when they're both 0, 0 or 1 is 1. That gives me out a 0. Nothing changed here, which means nothing changes here. And 0, 0, that's a 0, not 0 is a 1. So it won't change. And it would work the same way the other way, right? Where except it would be a 0 and a 1 down here with the 1 up here, right? So those are also stable states. It's only those two states that are marked with asterisks that are unstable for that brief moment of time until they become stable again. Because like the moment they become they're unstable and then become stable because they shift from this state to the next very quickly, right? Because as soon as it turns from 0, 1 to 1, 0, we're already at that state and it's stable. It happens like that. But there is a delay. And that delay that exists physically is one of the limitations we have with our computation systems, with our computers that we build. Clock speeds can only go so fast because of how long it takes for transistors to change states and stuff like this to happen. Is it clear when I say like this becomes unstable for the briefest of moments because once it changes to this, the inputs of the system become that, and it just turns into this next state immediately. Yeah? Happy, sad? Unhappy? Questions? Ask now. Now for fun, let's look at what happens if we set this to, they're both to 1. Let's say Q is 0 and Q naught is 1. We set them both to 1, what happens? Okay, 1, 1. All right, so we're trying to set and reset, or reset and set at the same time. Well, what's this mean? First of all, in terms of like the spirit of what this is supposed to do, set means set Q to high and reset means set Q to low. So when you say do both at the same time, that doesn't even make sense. But what would happen physically with this design? 1, 1, well that's a 1, we get a 0, and then 0 here, and 0, 1, that's a 1, that would become a 0, which means that becomes a 0, and then 1, 0, that's still a 1, and that becomes, oh, it's still a 0. And it would work the same way if we flipped it, right? Now, if we built this with NAND gates, don't quote me, but for some reason I feel like if we built this with NAND gates, this like undefined states behavior would be slightly differently. I think we would get 2 1s in the output. I could be wrong. Either way, this is an undefined state for this design. Try to disassociate, to get what I mean here. Like it's undefined. You're like, well, how can it really be undefined? Because I can implement it. The implementation and the idea are separate. The idea of the SR latch, how we want that functionality to exist, What would it mean to set and reset a bit to 1 and 0 at the same time? That's not a thing. That doesn't make sense, right? Maybe like oscillate? I don't know what's going on. Something weird's going on there. So that doesn't really make sense. But all the other functionality we want, we can implement with this, except we've got that funny situation where we can physically try to set and reset at the same time. And this is what its behavior would be. But at the end of the day, the whole point is don't set and reset at the same time. Don't do that. Because that's not what you're supposed to do with this thing. Like, yeah, I can take a shovel and try to hammer nails with it, but don't do that. That doesn't make sense. That's not the tool for that. Any questions about this? All right. Finally, if both S and R are high, the outputs are both 0. This is an invalid state. It's not reasonable to set and reset at the same time. Further, yeah, and that's the other thing that doesn't make any sense. How, like, these things must be inverse of one another, Q and Q naught. Yet apparently, if you try to set and reset at the same time, they both become equal. You can't do that. That's not valid. Okay? Like I said, one could do it, but there's no utility in doing that. You're just trying to be a jerk at that point. Okay. Activity. When the circuit turns on for the first time and all inputs are 0, what will the output of Q and Q naught be? Ooh, that's a fun one. When the circuit turns on for the first time and all inputs are 0, what will the outputs be? We don't have that condition here, right? Now, what would that mean? First of all, let me make sure the question is clear. This is not connected to power, all right? 0, 0. And set and reset are not going anywhere, right? So how will this behave? Take a moment and think about this. Seriously, think about it. You can figure this out, but it is kind of a funny exercise. If you're working on it, good, but consider the fact that what I've drawn here is like I've turned the power on, and this is the state of the system, and I hit pause. Not even a nanosecond has taken place. And you can look at this and be like, well, 0, 0, if you ignore 0, 0, you don't get a 0. How could that be dropped? Remember, nothing, like the time it takes to produce this output has not transpired yet. Okay? But when you hit go, it will. What's going to happen? You're looking shifty eye, like you're suspicious of something. No? No? You don't know? Here's another hint. There's a good chance you're thinking of this in an ideal scenario, but try to consider the fact that these things would be physically implemented. And all limitations of our physical reality would exist. Hope I'm not in anyone's way. Stop doing that. It's for everybody to know, not just you. Let's see what happens. So here is the set reset latch. When I hit run, consider the fact that this is 0, this is what I mean is going to happen. I'm going to hit run. What's going to happen? What's going to be high? What's going to be low? Oh, okay, I guess Q starts low. Let's try it again. Oh. Q went high. It went high. Maybe did we just see it wrong the first time? What's going on here? That state is unstable. If everything was happening perfectly synchronized, what would happen? Okay? 0, 0, or 0, 0, you get 0, you nod it, you get a 1. So this turns into a 1. And somehow magically at the exact same instance, look, the same thing would happen here. That turns into a 1, meaning that the input here is a 1 and the input here is a 1. 0, 1, that's a 1. Oh, that should, but then turn immediately back to a 0. Immediately back to a 0. And then immediately turn back to a 1 and turn back to a 1. And we're just going to go forever, except the time it takes for this, this gate, all of the transistors, to shift from one state to another. There is a time that it takes. It's not instantaneous. And there's a time it takes, and it's not instantaneous. And the time that it takes between this transistor and this transistor are probably not exactly the same. Meaning, one of these will change its state before the other, thereby making the system immediately stable. What I mean is, we have a 0, 0, okay? Let's say this bottom latch changes states just before the top latch. 0, 0, that becomes a 1. 0, 1, that becomes a 0. It stays as a 0. And we're set. Because one will finish before the other. These things won't happen at the exact same time. Where did I put my marker top? Does anyone see it? There it is. I think that's pretty cool. So to play around, though, with the SR latch, look, Q is 0. I can spam reset. Nothing changes because it's stable, right? 0, 1 is a 1. You nod it, you get a 0. 1, 1 is a 1. You nod it, you get 0. Either way, this won't change. Okay? You turn this to set. it changes because it became unstable for the briefest moments until it became stable again. Why is it stable? Well, look. The input, when I hit high, the input to here is 0. And a 0, 1 is unstable. But watch. Oh, I messed up. Let's, okay. Set, okay, there we go. Okay, here we go. This is what I want. A 0, and when I turn that to a 1, the input changed immediately to that other stable state. So it was only unstable for the time it took for this to become high. And then it became stable again. And that time it took is really fast. Pretty cool. And again, I can spam this. Nothing's going to change because it's already stable. And if I set them both high, well, there we go. For fun, let's see what happens. Let's just change these to NAND gates. Components, logic, NAND. Okay, run. Okay, reset. Something's not quite right. Maybe I have to invert the inputs. I can't remember how to do it with NANDs. Or maybe, yeah, I need to invert the inputs or something? Is that that's the trick with it? All right, well, there we go. Anyways, either way, SR latch. Activity time. Draw an SR latch. But I'm not going to, I'm going to leave it like this. Do it with NOR gates, but I won't include them here because I want to test you. And yes, this should be that trivial. And I'm going to stop the recording for now.